we have a parametrization. So if x is a function of t and y is a function of t, and we've got t between a starting point and an ending point, then we've really got a curve here. So as we change t on the side, t is the parameter, t is going from a to b. As we change t, then we see that our position changes in the plane. And our question is, how can we find the length of the curve, so the total distance that we would travel as we go from one time to the other, so the length, the arc length of this curve. In order to do this, we can use differentials again. Think about a small change in time. I'll just call it delta t. So time is changing here, and we want to estimate how much we move over. So we're here, and as we move over, the x value is going to increase slightly, and the y value is going to increase slightly. So the x value will go over by an amount delta x, and the y value will go over by an amount delta y. And so the distance traveled, the distance traveled here is going to be roughly the hypotenuse of a right triangle, where one leg is delta x and the other leg is how far up we went. Then the distance we went along that curve is going to be roughly equal to the hypotenuse. And of course the hypotenuse of a right triangle can be found from the two shorter sides, because the hypotenuse squared is the sum of the squares of the two shorter sides. So we get delta x squared plus delta y squared. Now these small changes in x and y can be found because we have these equations. They can be tied back to change in t because we have these equations. The change in x is going to be dx dt times the change in t. This is just the differential. The change in the output function, the output variable x, is going to be the slope of that function with respect to t times the change in t. By the same token, because y is a function of t, the change in y is going to be how fast y is changing times how much time has elapsed here. That means if you take delta x and square it, and take delta y and square it, then what you're really going to get is dx dt squared times delta t squared plus dy dt squared times delta t squared. So the length of this hypotenuse is going to be the square root of, let's see, both of these terms have a dx dt, so I was going to take, or have a delta t squared in them, so I'm going to pull that out. We've got dy dt, dx dt squared and dy dt squared, and then there's a delta t squared. This means delta t times delta t. Of course, the root of the product of two numbers is the product of the roots, so the amount that we move over, let's call it delta L, the length traveled in that little bit, is going to be dx, the square root of dx dt squared plus dy dt squared, all times delta t. This is now moved outside of the root because it was delta t times delta t, and that was underneath the square root. We just bring it out. So that tells us that if we make a small change in time, that we're going to travel a small distance delta L. To find all of those distances, what we should do is just add up all the small changes. So we add up all the small changes. Let's say we break this up into n little pieces, right? And then we just find the sum from I equals 1 to however many pieces. Each piece is delta L. So to make this better, we should take the limit as the norm of the partition tends to 0, which means that we should break this up finer and finer and finer so that our results are more and more accurate. When you do that, that's called a Riemann sum. We're taking the integral from the starting time to the ending time of dl. And of course, dl is related to dt in this way. Each little bit of length is equal to dx dt squared plus dy dt squared times dt. And this is the formula for the total length. So the total length would be the limit of this sum, right, which turns out to be this integral with respect to t. Let's look at an example of how you'd work with this formula. So we have this curve, and we want to find its length. So our starting time is 0, our ending time is 3. So the the first thing we calculate is dx dt. So to find dx dt, we have 2t plus 3 to the 3 halves power, all divided by 3. So the 3 halves is going to come down. We're going to get, we're going to have our 2t plus 3 to 1 power less, which is going to be 1 half. That's all divided by 3, and then we have times the derivative of what's inside. So by the chain rule, we get a 2 here, because the derivative of 2t plus 3 is just 2. And with a little simplifying, there's a 2 upstairs and downstairs, and a 3 downstairs and upstairs. So this is just the square root of 2t plus 3. Now dy dt is 1 plus, let's see, the root of t squared over 2 would just be t. Okay, so we know that the length is going to be the integral from our starting time. Just let me write the formula up here so you can see it again. The integral from a to b of dx dt squared, or x prime of t if you like Newton notation, dy dt squared underneath the square root dt. So in this particular case, we're talking about the integral from starting time to ending time. That's 0 to 3. We've got the square root of, if we square the square root of 2t plus 3, we get just 2t plus 3. If we square 1 plus t, then for a perfect square using the FOIL method, you'd get 1 plus 2t plus t squared dt. Now that's equal to the integral from 0 to 3 of, what do we have? We've got a t squared and a 4t and a 4 dt. And the key to integrating this integral is to notice that this is the integral from 0 to 3 of the square root of t squared plus 4t plus 4 is a perfect square. It's t plus 2 squared. So now that that's a perfect square, we've got the integral from 0 to 3 of the square root of this. Now technically that's the absolute value of t plus 2, but if t is going from 0 to 3, t is always positive, so t plus 2 is positive. So we don't need to worry about the absolute values. We just have t plus 2 dt. If we find the antiderivative of t, we have 1 half t squared. The antiderivative of 2 would be 2t. We just have to evaluate that between the two endpoints. And when we plug in 0, we don't get anything, so we can just find what we get at 3. So we have 9 over 2 plus 6. 2 times 3 is 6, minus, when we plug 0 in, we just get 0, so we just have to worry about this part. Let's see, that's 9 over 2 plus 12 over 2 makes 19 over 2. The length of this curve is 19 over 2. We'll do another example here. Remember the formula again. The length of the curve is the integral from starting time to ending time of the square root of dx dt squared plus dy dt squared dt. Okay, so let's find dx dt in this case. See, if you take the derivative of the natural log of a function, you get the derivative of the inside over the inside. Now the inside is secant t plus tan t, and the derivative of the inside, well, the derivative of the secant is the secant tangent, the derivative of the tangent is the secant squared. So we get secant tangent plus secant squared. We can simplify this a little bit because there's a common secant in the top and the bottom. Pull out that common factor, and then you're left with tangent plus secant, all divided by secant plus tangent. But you can add in any order, so this tangent plus secant is the same as secant plus tangent, so this is just secant. Oh, and I just remembered I left off part of the x. The other part of this derivative would be the derivative of minus sine, which is minus cosine. So we should have a minus cosine. So I end up with secant t minus cosine t in this problem. Now dy dt is easier. Dy dt, since y is cosine, the derivative of cosine is minus sine t. Okay, so our length should be the integral from starting time to ending time of the square root of, let's see, we've got secant t plus cosine t squared. Cosine t squared, that's dx dt squared, plus dy dt is minus sine, so if you square that you get sine squared t dt. Now if I multiply this out, I get the integral from 0 to pi thirds of the square root of, let's see, secant, if you use the FOIL method on this, you get secant times itself, so that would be secant squared. You get 2 times secant times cosine, but secant is 1 over cosine, so you're going to get plus 2, and then plus the cosine squared. Oh, I just made a mistake because that should have been secant t minus cosine t. So that would make this number minus. Okay, plus sine squared. Good. It was a copying error right there. But so when I square it, I get a negative sign here. The integral from 0 to pi thirds, and let's see. Negative cosine squared plus sine squared, that's 1. Negative 2 plus 1 would be negative 1. So we have the square root of secant squared t minus 1. But that's an identity as well, because the tangent squared plus 1 is the secant squared. So secant squared minus 1 would be the tangent, so tangent squared. So we have the square root of the tangent squared of t dt, which is technically the absolute value of tangent t, but since we're in this region where the angles between 0 and pi thirds, that's a region where tangent is naturally positive anyway. So we can write this as integral of tangent t dt. Now the antiderivative of tangent, since it's sine over cosine, the antiderivative of tangent, you could think of it as, see, the natural, think of it as a natural log. It's the natural log of cosine t with a negative out in front. You can just check that by taking the derivative, because the derivative of natural log is the derivative of the inside, which is minus sine, over the inside. So you have minus sine over cosine. That's minus tangent with another minus out in front. Makes it positive tangent. So we get the natural log of the cosine of pi thirds, negative natural log cosine pi thirds, minus minus would be plus the natural log of the cosine of 0. Let's see, the cosine of 0 is 1, and the natural log of 1 is 0. Oops. So we have that the length is the natural log of the cosine of pi thirds. Now the cosine of pi thirds is 1/2. We could simplify that just a little bit, because that's the negative natural log of 2 to the negative 1, and then because of the power rule for natural logs, that can come down in front. So we get positive natural log of 2 as the length of this curve.